Hello, I am Joe Bakos, welcoming you to this week's edition of the Taurus Report. I would like to, beginning with this episode, delve into the history of astronomy, cosmology, astrophysics, and sort of go through the standard presentation of the history of these subjects, and then show where CGC starts to differ from them. And for a while, of course, the account of astrophysics will be the same because many of the assumptions in standard astrophysics are the same as those for CGC. But let us go all the way back to the beginning, and because it is actually a very interesting story, a very interesting history. So let us go back to the ancient Babylonians and start with them. A natural question might be, why the Babylonians? Why go back to them? I think it's good to begin with that because it illustrates several of the common themes in astronomy, starting from the very beginning. The Babylonians speculated about, of course, as every generation has, where did it all come from? How did everything get started? And what is my connection to it on a personal level? And a lot of modern people aren't really conscious of this connection that the Babylonians saw, but let's just get into it a little bit. As most people know, a year is 365 days. Now, in ancient times, the Babylonians, they made a big deal about the number 60. One reason is because a lot of different numbers can go into it. 2, 3, 4, all these different numbers can go into it evenly. And why would they want to have a lot of numbers go into it evenly? Because when you're dividing time lengths and you're trying to make a connection, and what is an intimate connection to a human being and the cosmos in general, then it helps if you're dealing with a numbering system like that, where a lot of different numbers can go into it in a whole number way. So what do I mean by that? So, for example, 360 was the length of the year, 360 days. Of course, we'll say 365, but for them, they saw the year as 360 days, and then they would do little additional things to take care of the timing that didn't work out because it wasn't exactly right. But in any case, so you have 360 days, and then each day is made into 24 hours. Each hour is 60 minutes, and each minute is 60 seconds. Well, what's the big deal about that? Well, it turns out that 1 minute is about 60 heartbeats. And so there's a connection to the length of the year all the way down to the human heartbeat. And so there is always this attempt by the ancients to connect everything back to the human being, man being the measure of all things. So looking at the Zodiac, the Babylonians were the first ones to kind of divide the year into 12 different zones, depending on which constellations were most visible at night, and that changes over the course of the year. Let's take a quick look at that. Now, here's a representation of the Zodiac. For us, of course, we understand that, like, if this is the sun here at the center, and let's suppose this is the orbit of the Earth. Okay, so the Earth is going around the sun. So at different times of the year, when you look up in the night sky, different sign of the zodiac will be dominant depending on where the Earth is in its orbit around the sun. Now, of course, for the ancients, it's a little different in that they thought the Earth was at the center. And, well, let me just draw this on the other side. So the way the ancients kind of thought about all this is like, here's the Earth at the center, right? And then here's the sun. And according to Aristotle, the lights of the night sky, and the Babylonians thought something similar. Okay, so the lights in the night sky or day sky, like here's the sun, it would be in some sort of clear glass or sphere, and this sphere would rotate around the Earth. And so they saw the sun as going around the Earth. Now, anything that rotated, that had a different speed of rotation, they had to put in a different sphere. Like, let's say, here's the moon. And the moon would have its own sphere going around the Earth, because the moon moved at a different speed than the sun. And so if it moved at a different speed than the sun, then the moon would be in its own sphere. And then they had planets that were visible. You'd have a sphere for Mercury, a sphere for Venus. We'd have Mars, we'd have Jupiter, we'd have Saturn. So each of them, because they moved at a different speed, they had their own sphere. And then last of all, there would be the sphere that all the stars were in. Now, when I'm talking about the zodiac here, they would think that all of these stars are in their own sphere, like a glass sphere that rotates at a different speed around the Earth, right? Rotates at a different sphere. And then each of the planets that I mentioned, they would each have their own glass sphere that they were in. And they would, each of them rotate at their own speed, and that's why they need their own sphere. Now, because all the stars, to the ancients, they appeared to rotate around the Earth at the same speed, then they assumed that the stars, they were in the same sphere. And so, I don't know, how many does that make? Let's see, we got the sun is 1, the moon is 2, then we have Mercury, Venus, Mars, Jupiter, Saturn. So that's 7, right? And then there's the stars. So that's like 8 different spheres. And if you've ever heard the expression, seventh heaven or levels of heaven, when the ancients were talking about heaven, that's what they meant. If they said, you go to the 4th heaven or the 5th heaven or the 7th heaven, each sphere was its own heaven. And so we see how, for the Babylonians, and really for everyone else, all of the ancients, there was this deliberate and intimate connection with what was going on in the heavens to human beings. And so the wisest, or some of the wisest in any society, would be those concerned with looking at the night sky and trying to understand the origins of the entire universe and the way in which the universe operates, sort of in a mechanistic way. So if we look at things like Stonehenge, for example, you're talking about something 5,000 years ago, so like 3000 BC. So this was built and formatted deliberately to be able to predict eclipses. And so the ancients were very much concerned with all of this. Now, someone who came a little bit later, so the Babylonians, they kind of finished the Zodiac. Let's say the Zodiac was kind of finished in the form of having 12 signs in the sky. Maybe some of them weren't the same as the ones that we use nowadays, but some of them were. But in any case, that was finished, let's say, around the year 1000 BC, so something like 3,000 years ago. Now, around the year 100 AD, we have Ptolemy, and he wanted to take the prediction of the motions of the objects in the night sky, the planets and the stars and so forth. He wanted to take it to a new level of precision to predict these motions. And there was kind of a problem in that everything behaved as if it was on this sphere, like this perfect sphere, and it was all explainable that way, except for the planets. So the sun and the moon behaved properly, and the stars up in the sky, they behaved properly. But each of the planets had their own little problem called retrograde motion. So what does that mean? So let's take a look at the NASA site that kind of talks about this a little bit. So here it is. So if we take a look at this, and you're looking up in the night sky, like let's suppose you're following the path of Mars, and that's what this blue line is here. You're following the path of Mars, and it's going to go like this, over the course of a few weeks' time. Okay, and then its position in the night sky at a certain time. Now, when you're making observations like this, you want to observe them at the same time each night. So when I say Mars is moving like this, I don't mean it's moving, visibly as you're watching it this fast. That's not what I mean. What I mean is, like, if you observe it like once a week for several months at a certain time of night, you'll notice that if you look at the same time of night, it will be in a different position in the sky. And so what happens is Mars and the other planets, they exhibit this retrograde motion where they seem to be going forward for a while and then they go back for a bit, which is different than the stars. The stars don't do this. And then it resumes going forward again. And so in a modern sense, what is going on? Why is there this retrograde motion? In a modern sense, this is how we explain it, knowing what's happening. Like, let's say this is the Earth here, this circle, this inner circle is the Earth going around the sun. It is starting at position 1, then it goes to 2, then it goes to 3, 4, etc. So it's going this way. And then Mars is marked out where it is in its orbit at that same time. So at time 1, Mars is here. Time 2, it is here. Time 3, it is here. And you can see in relationship to that where Earth is at that same time. Now notice, because Earth is closer to the sun, it travels at a quicker speed than Mars. So eventually it kind of catches up to Mars, right? So the Earth catches up to Mars and passes it. So right in here, Mars appears to suddenly start going backwards, right? Mars starts going backwards. Now at this part in the orbit, the Earth is not moving so much in that direction anymore. The Earth starts entering into its curve here, right? And so then Mars, from our view, it starts appearing to go forward in its position again. And so because of that, right in this zone here, Mars appears to sort of reverse track and then starts going forward again. And in a modern sense, that is how we understand what we're looking at in retrograde motion. But how would the ancients explain that? Of course, they could say, okay, Mars is on this sphere, and every once in a while that sphere gets rotated backwards, and then it gets rotated forwards again. So they could arbitrarily just simply move that outer sphere. But the problem with saying something arbitrarily is that if you're going to just say it just arbitrarily moves this way, then you have to kind of give up on saying that it's working in like some kind of mechanism or machine, right? If you just say, well, sometimes it just, the gods like move this sphere backwards and then they move it forward again. Okay, and so then if that's the case, if it's an arbitrary act of the gods, then you can't really predict it, right? But it seemed to be predictable, and so Ptolemy wanted to come up with some kind of mechanism by which he could explain this retrograde motion. So let's take a look at what he came up with. What Ptolemy came up with was the idea of what's called an epicycle. So if this is Mars going around the Earth, because remember, to the ancients, the Earth was at the center of the universe and everything else kind of rotated around the Earth. So if Mars was going around the Earth, what Ptolemy did was he put it on what's called an epicycle. Instead of having Mars just traveling like this, Mars is itself traveling on some sort of a circle, some sort of glass sphere that is fixed to the other glass sphere, so that as Mars would circle the Earth, Mars was also circling on this sphere. And so we can see kind of an animation of that here. Let me try and show you that. Okay, so let me zoom out a little bit here. There we go. Okay, so that shows the motion. If this is the Earth, let's replay that. So if this is the Earth, then Mars would be going around the Earth on the large circle, but Mars is also circling on that epicycle, it's called. And this explained why sometimes the planets would have this back and forth motion. So to speak in round numbers, let's say the Babylonians, they come up with the length of the year and connecting it to the human heartbeat and the Zodiac, all of that around the year 1000 BC, so 3,000 years ago. Then we have Ptolemy, sometime around the year 100 AD, he comes up with a more precise way to make astronomical predictions, and he uses epicycles to explain retrograde motion. So then around 1500, again speaking in round numbers, we have Copernicus, who he came up with the idea of, he said, look, you have this epicycle approach to explain retrograde motion, but if you hypothetically, theoretically assumed that the sun was at the center of the solar system and that Mercury, Venus, Earth, and the other planets revolved around the sun, you would also be able to explain the various phases of the moon and Venus and everything, and also be able to explain retrograde motion in terms of the modern way of explaining it, as I've showed you. But Copernicus was hesitant to release this publicly. He only released it publicly near his death. I think he sort of foresaw the fact that if you started saying that the Earth was not the center of the universe, that was going to contradict Christian teachings and biblical teachings. And so he was kind of afraid of the blowback from all of that, which in hindsight he was probably right to be afraid. And so his work wasn't published until near his death anyway. So that's around the year 1500. So then again, speaking in round numbers, around the year 1600, we have Galileo with his telescope. He ground lenses and made a telescope. I don't think he was the first, but he was the first to do that and to make widespread observations. He discovered the moons of Jupiter and the fact that those moons were orbiting around Jupiter, and so that opened the possibility that things could orbit other objects and not everything had to be orbiting the Earth. And so then Galileo, he took up Copernicus's idea in a big way and said, yes, obviously the Earth did go around the sun, and this means that the Earth is not the center of the universe. And so he faced some vigorous persecution for that. Now, it wasn't until later, what we'll look at next, when we're starting to get into really, that's kind of the transition. I would say Copernicus and Galileo and next Newton. Those three are really represent the major transition into kind of a modern way of looking at astronomy and astrophysics. So let's take a look at Newton next. In some ways, Newton was following in the footsteps of those who went before, in the sense of trying to connect all of cosmology and the motions of the heavens to human beings. So what was the big advance that Newton made? The big advance was this law here. This law, the gravitational force is gravitational constant times the first mass times the second mass. Like if you're standing on the surface of the Earth, then the Earth would be the first mass and you would be the second mass, divided by square root of the distance between them. Now, if you're standing on the surface of the Earth, this means the distance between your feet and the center of the Earth. So even though you're in contact with the Earth, this r squared, the r is the distance. Even if you're standing on the Earth, the distance is not zero, because the distance is to the center of the Earth. In any case, this is Newton's big discovery. And I would like to say a few things about that. So first of all, what's the big deal? The thing that is innovative here and that really struck everybody at that time was that for millennia, people had looked at the skies and tried to come up with mathematical models to predict the motions of the heavens, to predict, where stars and planets, the sun, the moon, predict where they're going to be. Let's say 2 months from now, where will they all be? And so from the Babylonians on, you had all these calculations. And we saw even before that, the Babylonians, we have written accounts and history of it. But even if you go into prehistory, like Stonehenge was before that. And that is prehistory. And we can see even in prehistory that human beings were concerned with that kind of thing. Trying to connect themselves to the cosmos. Now, what Newton did was really like that, because he was explaining that the same force that is responsible for the motions of the planetary bodies around the sun, that same force is responsible for pulling you to the Earth. And he was able to put it in a mathematical form to model all these things with. And so he made that fundamental connection. I would say he brought the motions of the heavens down to Earth in a big way. Before going on, just one small digression. I want to talk a little bit about the meaning of epicycles in a modern context, because often theorists, when we're all arguing back and forth, everybody, of course, championing their own ideas, as I do, Everyone has their own ideas about explaining cosmology in this modern time, especially since there are several big challenges to cosmology right now, and everybody has their own ideas about it. But one of the things that we theorists do when we're arguing is we always accuse each other of the wheels within wheels, the famous epicycles. So Copernicus did away with Ptolemy's epicycles. And if you ever hear the phrase wheels within wheels, that's what that's about, because you have a sphere, like in Ptolemy's model, Mars was orbiting the Earth on a sphere. And then on that sphere itself, that sphere also had a wheel that was doing circles. And then when observations did not line up, then sometimes they would put wheels on those wheels to try and somehow come up with a mathematical model that was predictive. And so it is a great simplification often, and this is what theorists sort of dream of, is coming up with a new way of looking at things, an elegant way that simplifies explanations. And Copernicus did that when he went to the heliocentric model saying, hey, if the planets revolve around the sun, then a lot of these calculations would be a lot simpler. And so it was an elegant move to simplify calculations that turned it out to be correct in reality. And so often, to bring it up to a modern context, why am I saying all this? Is that you have, to explain some of the mysteries in astrophysics right now, you have kind of two main approaches. One that I criticize and I find nonsensical is the whole dark matter, dark energy, LCDM, Big Bang cosmology. That's one approach, and most astrophysicists nowadays subscribe to that, so I'm in a distinct minority. And then you have modified gravity theory, which is saying, hey, maybe our theory of gravity is wrong and the theory of gravity needs to be changed. And the thing that I find interesting is this. Both parties often, when they're talking about the other party, they say the other party is like using epicycles to explain things. And so both parties to this debate accuse each other of epicycles. And in that, I'm no different. I think dark matter and dark energy and the Big Bang and inflation and singularities, to me, all those things are epicycles, which are artificial crutches to try to make the calculations come out right, but which are not real. And I think that ultimately modified gravity is going to win out in a big way, and that things will be much simpler once we get to a force law. So anyways, that was my digression to explain the wheels within wheels and how people, modern debaters, are always accusing each other of, using epicycles or something analogous to epicycles. But I am going to bring it to a conclusion for this week. Now, next week, what I've decided to do is to go forward with the Taurus report, because there hasn't been that much new to comment on. If there's big news that's different than what I've covered so far as regards the Webb telescope, JWST, James Webb Space Telescope, and its observations, if there's new stuff that comes up, then I will bring that up in my episodes. Of course, there's been new observations and stuff lately, but in general, I'm finding that standard theorists are just stating the same old things again, to me, which are ridiculous, that we can form these kinds of galaxies this quickly. And standard theorists are refusing to give up the general relativity Big Bang model of the universe. And so, we'll see how extreme it gets. I mean, the further and further back we look, if they're seeing disk galaxies and spiral arms, large galaxies, further and further back, I mean, I have to wonder how far back must we find one before they'll finally admit, like, okay, that could not have formed since the Big Bang. From where we are positing the Big Bang is 13.8 or 13.6 billion years back. So, in other words, so that turned into another digression. Sorry about that. So, in other words, if something new, big and new, comes up from James Webb, I will cover that in the Taurus report, or any other observation in astrophysics for that matter. If something big comes up, I will cover it. However, until that happens, what I'd like to do is just continue developing the history of astronomy and astrophysics, and where I'm going to be showing what current standard theory is, and how it got that way, and what the CGC response to it is going to be as it develops. Now, I covered, which seems kind of unfair, I covered about 2,000 years of history, almost, just in one episode, and I'll have to greatly slow down going forward. We will start with the whole discussion, when Maxwell came out with his equations in the 1800s about the nature of light, and then with the Michelson-Morley experiment, how scientists kept searching for some medium for light waves to be moving through, because whenever you have a wave, you assume that there's some medium that is carrying the wave, what they called the luminiferous ether, which just means medium that would carry light waves. The same way, the ocean will carry ocean waves. They're assuming that there's some medium that must carry light waves. And so Michelson-Morley did the classic experiment trying to find that medium. And the failure of the Michelson-Morley experiment is what led Einstein and others to begin searching for some other explanation. Now, it turned out that Einstein's ideas, it's very interesting in that there's aspects of Einstein's ideas that I think are profoundly correct as far as, and I've gone over this in other episodes, but I'm going to delve into it a little bit more again, but this time go a little bit slower to show the actual development of this. So Einstein's ideas work very well to make certain specific predictions, such as the increase of relativistic momentum and time dilation. But I think that the idea, besides working mathematically, as many systems in the past that we later set aside did work, they did function to make good predictions. But then we found out later that reality, even though it worked as a good calculating mechanism, reality doesn't really match up with it. And so I will be explaining in a more meticulous and careful way, like exactly what in general relativity that I'm agreeing with and exactly what I'm disagreeing with and think needs to be changed. But delving into that whole discussion again with general relativity, that will be in our next episode next week, and I hope to see you there. Thank you. Bye-bye.